Site Planning and Design Handbook, 2nd edition by Thomas H. Russ. Site Data and Analysis, Chapter 3. In many respects, site analysis is the most important step in the successful site design process. The purpose of site analysis are to gather data for preliminary planning, evaluate the site for compatibility with the proposed project or use, recognize concerns requiring additional study, and form an understanding of the administrative requirements of the project, such as required permits and approvals. The value of the site analysis is in its clear and complete identification of issues and the character of the site as they relate to proposed use. The site analysis should be as far-reaching and broad in scope as feasible, but it is usually subject to fairly limited resources. Site analysis is a critical first step in planning and designing a site, but too often the value of a thorough evaluation of the site is discounted for the sake of lower costs or short time frames. Discovering site limitations or issues further into the planning and design process can be an expensive lesson. If such issues are discovered after design or in construction, the costs can be significant in economic terms and devastating to one's professional reputation. Very often, the initial site assessment is part of the proposal effort and is completed out of pocket, but the work should be thorough regardless of the fee because the professional will be held to account for the oversight. Even more troublesome is that the effectiveness of a particular analysis may be difficult to measure until well into design or even after site work begins. Corners cut or inaccurate assumptions made in the site analysis for expediency or economy may result in expensive rework and change orders during the design process, or worse yet, during construction. The site designer rarely has the resources or the time to complete a comprehensive site investigation on speculation of winning work. Therefore, site analyses are usually conducted in two steps: a proposal phase to facilitate winning the work and a post-contract phase. The proposal phase site analysis is extremely important because the proposal, sometimes even including preliminary design and costs, will be based on its outcome. As in-house resources provided for the assessment are usually limited, it is important that they be used carefully. The costs of collecting physical information must be found. Site characterization is a more detailed site investigation that is usually undertaken after some degree of preliminary site planning. Site characterization generally includes a geotechnical analysis of subsurface conditions such as depth to bedrock, depth to ground cover, seasonal high water table, and specific soil tests. The American Society of Testing Materials, ASTM, has developed a standard guide to site characterization for engineering, design, and construction purposes, D420. This guide provides the site designer with a consensus standard with which to plan and evaluate site characterizations. Chief among the concerns and underlying the analysis of a site is coming to an understanding of the environmental functions of the site. As site designers become more sensitive to the environmental impacts of their work and strive to offset them, it is important to have a clear understanding of the contribution made by the site. Location. The first consideration of the site analysis is to locate the site. Site location entails more than simply locating the site on a map. Location in this sense refers to the project's relationship to the community. Commercial projects are concerned about visibility, site access, and traffic. Is the traffic past the site adequate or is it congested? Is street infrastructure adequate for the anticipated increase? What sort of improvements might be anticipated? Is this site accessible from the street? What sort of on-site improvements might be expected to facilitate access? Is the interior of the site visible from the street? From how far away will drivers be able to see this site? Can traffic access site from both directions? Is a left-hand turn possible? Are the neighboring sites commercial or residential? Are off-site improvements required? Are the necessary utilities nearby? Residential projects have different concerns. How far away are schools, government, services, and shopping? Are local roads and streets adequate to handle increased traffic? Is the character of the area conducive to the proposed project? Will future residents be able to enter and leave the site without traffic congestion? Are adjacent properties developed? If not, what will zoning allow? Collecting site information. A number of existing sources of site information should be readily available within the office, and the internet gives a designer access to many other resources. This information is available in fairly specific forms and may contribute to the site analysis effort at little cost. Site analysis is an interpretive process. A broad array of information is collected from a fairly limited individual sets of information, and these data sets are combined to a project of a future use of the land. In general, preliminary site assessments are based on precious little new information. That is, much of the analysis is based on existing sources of information or first-hand observation. It is how the site information is understood and used that makes the difference in site analysis. Site analysis is not done in a vacuum. The context of the proposed use frames the scope and character of the effort. For example, among the most important considerations is the topography of the site. Sites with significant change in elevation are typically difficult and more expensive to develop. Of course, the same steep slopes that are a source of concern for the commercial builder may be the bread and butter of the resort or high-end residential developer. Topography. The United States Geological Survey, USGS, is a valuable source of topographic information. A local selection of the 7.5-minute quadrangle series of topographic map is found in every design office. The amount of detail and relative accuracy for the cost is difficult to improve upon. USGS maps are available from a variety of sources, including the internet. www.usgs.gov. Commercial sources of topographic information are available at websites operated by firms working in partnerships with the USGS on a variety of projects. Even more convenient are free sources of topographic information now found on the internet. The most basic element of site analysis is the lay of the land. The topography of a site may dictate the purposes for which the site may be used, and eventually the layout of the proposed project. The location of the buildings and roads, pedestrian circulation, and the arrangement of stormwater features are all commonly affected by topography. The analyst must consider how the existing topography affects the proposed use. Although the contour intervals are fairly large, the relative accuracy of the quad maps allows for interpolation for general planning purposes, but not for design. The preliminary analysis of the site provides an early look at how the proposed development will fit into the site. Will significant earthwork be necessary? Will retaining walls or other appurtenances be required? Can the site be accessed from adjacent roads? Is there visibility into the site from adjacent roads? The nature of the material making up the slope is also important. A soil survey may provide important information pertaining to the erodibility of soils and the risks associated with cotton field operations. Removing established vegetation from slopes may create unstable conditions, requiring additional engineering and construction costs. Many land development and zoning regulations include restrictions on the development of steep slopes. More detailed information on soils is provided later in the chapter. A slope analysis is done to identify the areas of steep slopes and the possible location for building sites and access. The slope analysis is usually a graphic representation of slopes shown in classes or ranges. The ranges are sometimes established by local ordinances which describe the parameters to be observed when conducting a slope analysis in steep slope development restrictions. The slope analysis may identify possible routes for on-site traffic circulation as well as drainage patterns. The restrictions imposed by slopes become more apparent when examining a finished slope drawing. Development patterns that are in tune with the site will be clearly evident. From a hillside, the long views are generally considered the most valuable. A site analysis should include identification for the long views and any obstructions or limitations to them. Site development should proceed with the maintenance and optimization for the long views in mind. Undesirable views should also be identified and addressed in the analysis. The approach to the site and the actual means of access onto the site are key elements. The best paths of circulation, the minimization of impact on the site to develop these networks, and the extent of required cuts and fills all must be considered. Existing design requirements in ordinances may require revision to make the hillside project work. What works on a flat site may not work on the hillside without extensive earthwork and disturbances. Site distance for egress to public roads should also be considered. Other elements of the site analysis include the identification of canyons, wetlands, rock outcroppings, existing structures, unique habitats or natural features, neighboring land uses, and utility locations. Flat and low areas present their own concerns. Boggy or wet areas may be wetlands and restrict development. Sites are low or flat may be difficult to drain and present difficult design challenges of their own. The location of rights of way, easements, and the other encroachments is also important. Findings of the site analysis may indicate that further research or study is required to determine the stability of slopes, hydrologic conditions, or the extent of wetlands. The site analysis is the foundation of the plan. It will provide the framework from which the planning and designs are developed. The aspect of the site may also be an important factor. Orientation toward the sun may influence how well selected vegetation will perform and will affect the performance of buildings as well. North-facing slope will be cooler than a south-facing slope. A southwestern exposure may be quite hot in the summer. The implications of aspect can be translated into energy consumption and the other features of the development. Building orientation is becoming a more important factor as global climate changes and energy efficiency concerns rise. In addition to topographic maps, the USGS can provide aerial photographs, digital orthophoto grad-angles, and other high-quality sources of site data, and a number of websites offer free aerial photos. Through the Center for Integration of Natural Disaster Information, CINDI, the USGS has a greater deal of information about regional and local site hazards such as earthquakes, landslide risks, groundwater conditions, flood risk, and more. The USGS also has information about site geology, a series of geological maps and information on geological hazards, sinkholes, slides, and earthquakes, faults, etc., is based on the topographic quadrangle maps. These maps include paleontological information as well. The USGS completed a survey of the biological status of the United States in 2000, which includes information on endangered as well as exotic invasive species. USDA plant hardiness zones. The USDA updated the plant hardiness zone map, so familiar to growers and planters, in 1990 and reformatted the map in 1998. The new version incorporates new temperature information by using coldest weather data from the years 1970 to 1986. The map introduces a new zone, Zone 11, which is essentially a frost-free zone. Discussion of the plant hardiness zone map is included in the section on zone analysis to encourage landscape architects and site planners to consider potential impacts of global change in their evaluation of a site. It is estimated that warming trends may have significant impacts over the next 100 years, with notable changes occurring by 2025. These changes may significantly affect the performance of designs under consideration today. Although no broad consensus as to how to address these concerns in design is on the boards, designers should begin to consider incorporating the most likely scenarios and trends in their work. Trends in climate change raise different concerns for various parts of North America. FEMA maps. The Federal Emergency Management Agency, FEMA, is best known for the flood maps it has published over the years. Just as the USGS is more than topographic maps, FEMA provides much more of the site analysis process than flood information. FEMA maintains a website that allows the designer to create a fairly site-specific map of hazards related to earthquake, tornadoes, wind, and hail, as well as floods. FEMA's website, www.fema.gov, includes a number of valuable links, one specifically for design professionals' questions. Unfortunately, FEMA does not yet provide flood insurance maps online, but maps may be purchased in either paper or digital form through the website. FEMA does not provide information on changes to the existing maps on its website. Vegetation. An assessment of existing vegetation may tell a designer a great deal about a site. Evidence of second growth vegetation is an indication of past activities that should be reconciled by the analyst with the other sources of information. If the site indicates significant disturbance from past activities, there should be a record somewhere of what those activities were. The quality of vegetation is also an important consideration. Quality specimens of trees or a valuable population of another type of plant should be protected or incorporated into a future design. The presence of water-tolerant plant species may indicate a high water table or frequent flooding, whereas poor quality or stressed vegetation may indicate problematic soil or subsurface conditions. Prior to making a site visit, the analyst should consult local or state sources for information pertaining to protected plant species. In many cases, the location of populations of protected species is mapped by these agencies. The discovery of such a plant population or community could have a significant impact onto the future use and development of the site. Trees or tree masses may contribute value to the finished project, and their location must be considered in the assessment. Mature trees are known to increase the market value of property, and a qualified arborist should be asked to assess the condition of specimen trees to determine their relative value. A variety of evaluation methods are available, but they generally have these elements in common: the type of tree and the characteristics of the species, as displayed by the specimen, such as form, color, shape, and condition. James Urban has developed a practical and usable approach to tree evaluation. This method was specifically developed for city trees, but the fundamental approach can serve as a guideline in evaluating the trees on a given site, particularly during the early site analysis stage. Table 3.1. 1. Excellent condition. No noticeable problems. Branching is irregular and even. Normal sized leaves, normal color. Good condition. Full grown with no tip dieback, minor bark wounds, thinner crowns, slightly smaller leaf size, or minor infestations. 3. Fair condition. One or more of the following. A. Minor tip or crown dieback, less than 10%. B. Small yellowed or disfigured leaves, thinner crown. C. Significant limb wounds. D. Recent large branch removed that minimally affects shape. Large insect infestation. F. Any problem that should be repaired without long-term effect on the plant's health. 4. Poor condition. Any of the following. A. Crown dieback from 10 to 25%. B. Significantly smaller yellowed or disfigured leaves. C. Branch removal that affects the crown shape in a significant way. D. Wounding to the bark that will affect the tree's health. 5. Very poor condition. Any problem that is so significant that it grossly affects the shape or the health of the tree. Tree that has little hope of survival. 6. Replace. Some green may be seen, but the tree is not going to survive. 7. Dead. Source: Urban, James R. Evaluation of tree planting practices in the urban environment. Proceedings of the 4th Urban Forestry Conference, paper presented at the 1991 annual meeting of the American Society of Landscape Architects. Aerial photogrammetry. Aerial photogrammetry provides an accurate mapping of the topographic and physiographic features using low-level aerial photography. The topography is interpolated from limited topographic data collected on the ground. Properly prepared photogrammetry meets national map accuracy standards and may be significantly less expensive than traditional field topographic methods, especially on large projects or projects with significant topographic variation or many features. The ability to collect aerial photography may be hampered by vegetation that obscures the ground and therefore may only be collected during winter months in some areas. The cost of photogrammetry prohibits its use in the preliminary analysis stage, but many municipalities have photogrammetric information available for review. Historical aerial photography. Unlike photogrammetry, existing aerial photography can be a valuable source of information for the site designer at a relative low price. Private firms may have generations of aerial photography taken on speculation or on contract. Many communities also have collected aerial photography over the years. Some state geological surveys and the USGS also have historic aerial photography available for purchase. The American Society of Testing and Materials, ASTM, has developed a standard guide for acquisition of file aerial photography and imagery for establishing historic site use and superficial conditions. The guide can assist in the identification of public sources of existing aerial photography as well as provide information regarding the specifications of such photography. Public sources of photography are helpful, but many private sources exist as well. Private firms may be willing to work with the designer to enlarge and prepare special prints of photographs. Photography firms may be reluctant to enlarge photography to scales useful for the site planners because of the inherent distortion and inaccuracy that can be anticipated in the resulting print. But these enlarged photos are a valuable planning and analysis tool. The most accurate part of the photograph is the center of the lens. The curvature of the lens results in minor distortions towards the edges and corners of the picture, and increases as the photograph is enlarged beyond the intended scale. Such enlargements are of limited use but may be adequate for preliminary planning purposes. Enlarged aerial photographs sometimes reveal site features not clearly visible at ground level, such as drainage patterns, sinkholes, and the remains of historic structures. Old aerial photography may reveal features that have been obscured by later site activities or development. An aerial photograph is also helpful in presenting the site analysis data to clients and others who may not be comfortable reading plans. A series of historical aerial photographs show the site conditions at one site at 3 different times in the past. USDA Soil Survey. Soil surveys have a compendium of valuable information. Soils are classified as series, and these types are further refined into detailed soil map units. The soil descriptions include information on slope, depth to bedrock, soil texture, erodibility, rock, and drainage characteristics. Figure 3.4. Soil maps are generally accurate, but occasionally field observations indicate soil conditions at odds with the survey. In such cases, local Natural Resources Conservation Services (NRCS) offices can be helpful in resolving the discrepancy. USGS soil surveys are now available online. Although soil borings and test pits may be done eventually, the site analysis may use existing sources of information such as the local soil survey or a previous soil analysis. In addition to describing the character of the soil survey includes information about different management techniques, engineering characteristics, and uses for the land. For the site designers, charts describing the engineering and development capabilities of the land are an important part of the soil survey. Each local soil survey includes a description of how the survey was made and how to read the survey. Hazardous soil conditions. Expansive soils occur in every state, and these soils may cause extensive cracking of sidewalks, foundation failures, retaining wall failure, and so forth. Table 3.3 outlines the characteristics of expansive soils under wet and dry conditions. Liquefaction, a condition in which solid ground can turn mushy when soils are vibrated, is also associated with earthquakes under certain conditions. Soils lose all bearing capacity. Buildings or bridges can slip or sink, like quicksand, and buried structures can float to the surface. Tanks. These conditions have been associated with fine to medium-grained sands and silts found in loosely packed layers. In general, the greater the soil density, the lower the liquefaction risk. A clay content of 15% or more is adequate protection from liquefaction. Another form of liquefaction is found in quick clays, which can become quick or liquefy. Confined to the northern states and Canada, New York and Vermont have had quick clay failures. These very fine flour-like clays are formed as sediments in shallow waters and later raised above sea level. Collapse of quick clays has been associated with high water content. As the material weight exceeds its shear strength, slope failure results. Hydrology. The presence of water on the site and the general pattern of drainage are key concerns of the site analysis. Water is often the key feature of a site. Waterfront, the presence of a stream or pond brings added value, but it also raises concerns for development. The presence of a surface of water feature may be coincidental with a fairly high water table or shallow geological features. Drainage patterns should be carefully observed in the field as well as being examined in published sources of information. The presence of associated wetlands and floodplains must be preliminarily located, and the location and extent of riparian zones should be noted. The location of water features and other hydrological linked features of the site should be carefully observed and evaluated. It is important to locate and identify springs and seeps in the site analysis process. Very often these features are located on USGS maps or soil surveys, but the analyst should confirm their presence in the field. It may be appropriate to consider local off-site hydrology as well. The analyst should consider stormwater drainage on the site as well as drainage from the other sites onto the subject site. Of particular concern are the volume, concentration, and quality of runoff stormwater. Sites located along streams in the lower reaches of the watershed may be affected by conditions higher in the watershed. Begin to identify stormwater management strategies in the site analysis. The drainage pattern of the site and the presence of water features will indicate the likely location of stormwater collection facilities. The site analyst should consider the sensitivity of hydrologic features to development. Erosion and sedimentation during and after construction may represent a serious threat to surface water quality and habitat. If significant measures will be required to protect surface waters, this should be discussed in the site analysis. Many states have programs designated streams and lakes of high quality and providing special protection measures for these waters. Determine whether receiving waters are high quality or restricted and how their status might affect the project. Under dry conditions, soil is hard, resists penetration by knife blade, and is difficult to crush by hand. A cut from a shovel leaves a shiny surface. A surface may display cracks in a more or less regular pattern. The width and spacing of cracks indicate the relative expansion potential of the soil when wetted. Surface irregularities such as footprints and tire tracks cannot be obliterated by foot pressure. Under wet conditions, soil is very sticky and will accumulate on shoe soles to a thickness of 2 to 4 inches when walked on. Soil can be molded into a ball by hand and will leave a nearly invisible powdery residue on hands after they dry. A knife or a shovel will penetrate the wet soil quite easily, and the cut surface will be smooth and tend to be shiny. Freshly machine-scraped or cut areas will tend to be smooth and shiny. Heavy construction equipment such as bulldozers and compacting rollers will develop a thick soil coating which may impair their function. Adapted from Gary B. Griggs, Geologic Hazards, Resource and Environmental Planning. Table 3.3, Recognition of Expansive Soils in the Field. In addition to sedimentation issues, the non-point source pollution programs of the National Pollution Discharge Elimination System, NPDES, have required municipalities to re-evaluate stormwater management schemes. The need to establish total maximum daily loads for affected waters may result in more stringent design requirements in the coming years. Local records and history. Land use planning and development is generally an issue and concern for local government. Local governments very often have substantial information about a site, as discussed in the preceding sections. Aerial photography, mapping, and other physiographic information is often available from local governments. The regulation of land use, however, is usually done at the local level. Zoning. Of all the local sources of information, zoning regulations are probably the most important. Zoning regulations provide a prescription for how development is to be done in a community. The general condition of development are described in terms of what development is encouraged and where in the community it will be. Zoning maps provide an overview of the community's vision for itself, not only indicating how a site may be developed or used, but also how surrounding sites might be used. Zoning regulations may contain design criteria, such as parking configuration, lot sizes, setbacks, road width, road profile restrictions, and sign requirements, to name a few. Local regulations may also include specific performance requirements such as noise, solar access, or pollution loading restrictions. Zoning ordinances restrict development by providing the limits and conditions of development, but they facilitate development by providing developers with a guidance document. A clear evaluation of the zoning particulars of a site is a critical requirement for a complete site analysis. Occasionally, zoning may include overlay zones that have important implications for land use. Overlay zones such as steep slope restrictions, watershed protection, historical preservation, or aquifer protection may severely limit land development activities or require a higher order of performance from the design, construction, and operation of a site. Land development regulations. The scope of a land development regulations varies widely from place to place. Very often, these regulations reflect an evolution of practices as much as they reflect a cogent regulatory process. Local ordinances are most valuable because they provide a glimpse into the experience of municipality by reflecting their concerns and bias. Some ordinances are very prescriptive, others are concerned more with performance. In any case, understanding the local land development ordinances is second only to understanding the zoning regulations. Land development regulations typically include requirements for local street design, open space, lighting, subdivision standards to be considered in conjunction with the zoning requirements, minimum landscaping, and similar site development parameters. The primary differences between zoning and land development regulations are in the underlying authority. Local officials may have the authority to waive or modify provisions of the land development ordinance on a case-to-case basis, but zoning regulations are enforceable and cannot be waived without justification and a formal hearing process. Although procedures exist to provide for variances and exceptions to zoning ordinances, these procedures are formalized and offer little latitude to zoning hearing boards. Zoning requirements of initial concern include the permitted uses, density, minimum lot sizes, setbacks, and open space. Care should be taken to consider the effect of wetlands, floodplains, or other site conditions that might influence the useful areas in terms of density and proposed site. Some zoning ordinances require special setbacks between different types of uses, such as a buffer area between residential and commercial land uses. The requirement for buffers, screening, and open space should be noted. Utility mapping. Location of utilities is made possible using maps provided by local utility companies. Increased use of geographic information system has helped to provide reasonably accurate utility data in most places. However, utility maps generally are not considered accurate, and locations should be confirmed in the field for design purposes. Historical value. Historical society and agencies may have important site information. Identification of historic and archaeological elements is very important because most states have regulations protecting historic or archaeological materials and site. Discovering that a site has a historical feature or value is a critical piece of data in the early analysis. Sources of information regarding the features include local and state historical agencies and societies, local government records, USGS maps, and libraries. Sometimes local names for features such as bridges and roads are indicators of a historical cultural element of value. Historical sources often have informative value as well. Place and road names can provide insight into former conditions and uses. A site located on Swamp Road, for example, could suggest a seasonal flooding or wetland conditions not evidenced at the time of a site visit. Local historic cultural values are sometimes hard to discern. Written information may address the physical area of the value but not address the community's attachment or less tangible values such as of use or local character. These values are often unwritten and informal, but they may represent a significant, albeit unofficial, community interest that should be addressed. Though more difficult to identify, analysts should be sensitive to community values. Infrastructure. The location of a surface and subsurface utilities is part of the site analysis. The analyst should identify the location, capacity, and access for all necessary utilities, as well as the requirements for connections. Of a particular importance might be moratoriums or sanitary sewer or water connections or exorbitant connection fees. Equally important is a consideration of the interferences between utilities either on the site or in bringing the utilities to the site. Access to public water and sewer should be evaluated. The capacity of existing water and sewer may be of concern in some communities and should be evaluated at an early stage. The capacity of road networks to accommodate proposed traffic is also a concern. Are local roads of a type and design sufficient for the proposed project? Are turning radii adequate? Will traffic signals and other improvements be necessary? Requirements to upgrade public highways may be prohibitive for some projects. Assessing fit. Fit is difficult to define, but like quality, you will recognize it when you see it. In some places, fit is as simple as reading the zoning and local development plans. In other communities, assessing fit is more difficult. In general, fit is determined by how the project design and function fits into the local zoning. Land development plans, the physical aspects of the site itself, the neighborhood, occasionally the region, and finally the values and needs of the community itself. It could be argued that these elements are listed in order of increasing difficulty for assessment and accommodation. Program requirements. The process of collecting site information is much of the same for every project, but the analysis is always performed in the context of a proposed use of or project. It is necessary to have an understanding of the proposed project when conducting the site analysis. In most cases, the designer must rely on the client and the experience to form a working understanding of the proposed project. Projects with a poorly defined program should be addressed cautiously by the professional. Experience suggests that a high risk of failure is often associated with such projects. Disappointed clients and unpaid invoices seem to accompany poorly defined or considered projects. Occasionally, designers are asked to evaluate a site for its possible uses, in which a case of series of analyses are done presuming different uses and parameters. But in most instances, the analysis is conducted with an end use in mind. The analysis must consider the fundamental elements of a given project, such as the site of proposed buildings, access to and from the site, lot layout, parking requirements, vehicular and pedestrian circulation, and a general strategy for stormwater management. Physical development constraints such as slopes, wetlands, and floodplains must be accounted for in preliminary fashion. Site analysis should extend their efforts to consider the off-site issues as well, which may include traffic issues, local floods, stormwater concerns, or infrastructure issues. Permitting and administrative requirements are particularly important in contemporary site development. Knowing which permits are necessary and the expected lead time required is often critical in an element in a project. The professional should attempt to assess the desirability of the project to local government and people as well. ADA and pedestrian access. The Americans with Disabilities Act, ADA, became a law in the United States in 1990. Under the act, that a person with a disability is entitled to the same access and accommodations as the public in general. As a result, building and site owners were required to remove barriers wherever such an accommodation was considered readily achievable. The readily achievable test can be ambiguous for existing buildings, but for new construction, it is clear that all public accessible designs must incorporate ADA principles and requirements. The Americans with Disabilities Act Accessibility Guidelines, ADA AG, were promulgated by the Architectural and Transportation Barriers Compliance Board. These guidelines are available on the ADA AG website. Although many of the design conventions of ADA have become commonplace, site designers may want to consider forming a preliminary analysis for the accessibility issues that may be encountered. It is recommended that designers confirm standards with an updated government source. Proposed changes to some of the ADA site standards have been made public for comment but were not yet approved by the time of this writing. Most of the proposed changes are concerned with buildings, but for changes related to site work, for the most part, details in this book reflect the proposed changes to the site standards. ADA issues regarding open space, recreational facilities, historic landscapes, or steep sites may present particular design challenges. It is not too early to be thinking about these issues and their impact on the design. Community standards and expectations. Community standards and expectations are usually unwritten and often ambiguous, but they can be very important considerations in the site analysis. Site designers may intuitively be able to assess the expectations of community by observing what has been accepted in the past. For example, what does a community and neighborhood around the site look like? Standards for plantings, architectural elements, styles, materials, and how pedestrians and vehicles are treated in the existing design all compromise standards and expectations that often exceed written ordinances. Loss of locally used open space or of access to other land might engender resistance to a proposal by the community. Anticipating and addressing these expectations in the early phases of design may contribute significantly to the project's acceptance by the community. Environmental concerns. In the recent past, site analysis necessarily expanded to include at least cursory assessments of the environmental conditions evidenced on a site. Environmental, in this sense, refers to the narrow considerations of past industrial or commercial activities and their impact on the site. An analyst should be aware of conditions that may indicate environmental contamination. Another environmental aspect of growing concern to site designers is the impact of environmental trends, such as global climate change and its anticipated impacts, and the growing demand to incorporate sustainability into site development. In particular, site designers working in coastal areas are subject to tidal influence, or in areas with important hydrological characteristics such as wetlands or cold water fisheries may wish to consider the anticipated impacts. Designers may choose to incorporate these impacts into the selection of plant types and design considerations. Beyond these concerns is a need for a deeper understanding of what the site does systematically in the environment that is a part of a larger landscape. Elements of the landscape provide particular environmental services ranging from habitat to temperature modification. The site assessment process must grow to accommodate this sort of ecological services analysis. Table 3.4. The ability to understand the contribution of landscape complexity and to measure these functions of the landscape in terms of environment, quality, and economic value has improved dramatically. Table 3.4, Ecological Services Analysis. Identify vegetative communities, presence of native and non-native species, presence of invasive exotic species, biological diversity. Habitat seasonal and year-round, presence of colonial birds, erosion protection services, stream wetland protection services, hydrology, surface water present, water purification services, flood buffers, seasonal hydrology, wetlands, riparian functions, groundwater recharge, soils, nutrient transfer, permeability, soil structure, soil productivity, local climate, windbreaks, temperature modification. There is a corollary to preserving the environmental functions of a site, and that is a more complete understanding of the impacts of the proposed change to the site. In most cases, the environmental impact of development is not limited to a loss of environmental functions, but has a broader impact that is worthy of our attention. Another sort of assessment is necessary in the planning stage if we are to build sustainable sites. The question is raised by these concerns will be discussed throughout this book. Environmental site assessment. The legacy of our past industrial waste disposal practices and experiences like Love Canal prompted lawmakers to pass environmental laws to protect the public and to compel landowners to pay for the cleanup of their property. Today, prudent real estate buyers and nearly all lenders require an environmental site assessment (ESA) of a property before committing to a purchase. As with any aspect of real estate development, planning is a key to managing this process. An ESA is a risk assessment used in the planning and feasibility stages of a real estate development. Assessments are used to evaluate all types of property, virgin land, recycled land, and renovation properties for conditions that are indicative of possible environmental contamination. The presence of actual contamination could trigger liability for the costs of site cleanup and restoration for the owners and users of the property. By identifying the conditions prior to purchase, a buyer can avoid or minimize exposure to the costs of remediation. Lenders want to limit their exposure to lawsuits and liability for cleanup responsibilities and will demand full disclosure of any known contaminants or conditions. The information in the site assessment report should identify any recognized environmental contamination and describe what further steps might be required. Environmental site assessments are also performed in conjunction with applications for liability protections or release under various brownfield statutes and regulations. A more detailed discussion of environmental site assessment is provided in App A. The most common and widely accepted site assessment protocols are those developed by the American Society for Testing and Materials, ASTM. These consensus standards are developed by practitioners and users of ESAs. The Standing ASTM Committee meets periodically to consider and occasionally revise the standard guidelines to reflect current practice. See Appendix B. ASTM has developed a variety of assessment protocols focused on various assessments activities. A partial list of the assessment standards that may have application in site planning and design is provided in Table 3.5. ASTM Standards for Site Assessment, Table 3.5. E1528, Standard Practice for Environmental Site Assessment Transaction Screen Process. E1527, Standard Practice for Environmental Site Assessments, Phase 1, Environmental Site Assessment Process. E1903, Standard Guide for Environmental Site Assessments, Phase 2, Environmental Site Assessment Process. D6235, Standard Practice for Expedited Site Characterization of VADO Zone and Groundwater Contamination at Hazardous Waste Contaminated Sites. E1984, Standard Guide for Process of Sustainable Brownfields Redevelopment. E1861, Standard Guide for Use of Coal Combustion Byproducts in Structural Fields. D5746, Standard Classification of Environmental Condition of Property Area Types for Defense-Based Closure and Realignment Facilities. E2991, Standard Guide for Use of Activity and Use Limitations, including institutional and engineering controls. D5730, Standard Guide for Site Characteristics for Environmental Purposes, with emphasis on soil, rock, and the VADO's zone and groundwater. D5745, Standard Guide for Developing and Implementing Short-Term Measures of Early Actions for Site Remediation. E1923, Standard Guide for Sampling Terrestrial and Wetlands Vegetation. E1912, Standard Guide for Accelerated Site Characterization for Confirmed or Suspected Petroleum Releases. E1689, Standard Guide for Developing Conceptual Site Models for Contaminated Sites. E1624, Standard Guide for Chemical Fate in Site-Specific Sediment Water Microcosms. D6429, Standard Guide for Selecting Surface Geophysical Methods. D6008, Standard Practice for Conducting Environmental Baseline Surveys. D5928, Standard Test Method for Screening of Waste for Radioactivity. D5745, Standard Test Method for Screening of Waste for Radioactivity. D5745, Standard Guide for Developing and Implementing Short-Term Measures of Early Actions for Site Remediation. D5717, Standard Guide for Design of Groundwater Monitoring Systems in Karst and Fractures Rock Aquifers. D420, Standard Guide to Site Characterization for Engineering, Design, and Construction Purposes. D551894E1, Standard Guide for Acquisition of File Aerial Photography and Imagery for Establishing Historic Site Use and superficial conditions. Why perform a site assessment? Environmental site assessment has become a common practice because of the risk purchasers assume when they take ownership of a property. Under the Federal Comprehensive Environmental Response, Compensation and Liability Act, CERCLA, a landowner is liable for the environmental conditions on the site, whether the individual or company had any knowledge or involvement in the condition. This liability can include costs of cleanup as well as damages to third parties. The Small Business Revitalization Act has given some important relief for landowners, but caution is still advised when purchasing property. The law provides buyers with several avenues of defense from this liability. These include acts of God and the innocent landowner defense. The innocent landowner defense is available to parties that can demonstrate that prior acquiring a property, they had no knowledge of or reason to know of any adverse environmental conditions. They would demonstrate that they undertook an investigation into the historical use and current condition of the property and could find no indications of environmental contamination. This investigation would have to meet a standard of due diligence or customary commercial practice. Buyers of commercial property and lenders minimize their risk by engaging an environmental profession to complete an investigation. Eventually, the consensus standard emerged as means of evaluating this good commercial practice. Site professionals may have an additional interest in ESA because of the potential for late discovery of an environmental condition to disrupt the design and development process. Further, site design professionals might elect to fold elements of the site assessment, a transaction screening, into their own analysis of the site. Format of a site assessment. Typically, a transaction screen and a Phase 1 environmental site assessment should be conducted before title is transferred. The Phase 1 environmental site assessment requires the services of an environmental professional. A transaction screen may be performed by a person with knowledge of land and real estate, and site design professional has adequate knowledge to conduct this analysis. The professional can purchase a pre-printed checklist from the ASTM that provides the entire standard guidelines E1528. Using the checklist, the site professional can walk through the cursory site assessment process as part of the on-site analysis. Information collected in the screening process could contribute to the site analysis by identifying additional concerns that might affect the proposed use. The outcome of the site assessment may be to recommend that the client conduct a Phase 1 environmental site assessment. Very often, lenders require Phase 1 environmental site assessment as a minimum acceptable level of investigation, and the transaction screen may be used to provide a guidance. The screening process is a straightforward evaluation of the property, which is most appropriate for properties where no development has occurred. Despite these limitations, the site professional should consider adding the screening to the typical site analysis. Some lenders have an in-house screening process, but the ASTM Transaction Screening Guide E1520 is the most commonly used format. Table 3.6 describes the level of inquiry common in an environmental screening. Table 3.6 Level of inquiry for an environmental screening. Has the site been filled in the past? Is there any knowledge that the fill could contain hazardous materials or petroleum waste products? Is the property in an area currently or historically used for industrial or commercial activities? Is the property zoned for industrial or commercial uses? Are adjacent properties used for industrial or commercial activities? If there are existing or previous commercial or industrial uses, was there any indication of hazardous material may have been used, generated, stored, or disposed of? Does the site drain into municipal collection system? Do adjacent properties drain into the site? Are there reasons to suspect the quality of runoff from adjacent parcels? Are there transformers on the property? Is an on-site well required for water supply? The Phase 1 environmental site assessment. Several factors contribute to deciding to perform Phase 1 environmental site assessment. First, if the buyer is a professional developer or a personal person familiar with the real estate, it is likely that the buyer would be held to a higher standard of inquiry than a simple home buyer. This is probably true of site design professionals as well. Second, if a site has been used for industrial or commercial activities, it should be assumed that there is a greater chance that hazardous material may have been used or stored on the property. This increased risk would compel a greater level of inquiry. Finally, many lenders require Phase 1 environmental site assessment as a minimum level of inquiry. The Phase 1 environmental site assessment process is usually completed by a qualified environmental professional, although some states have defined the minimum qualifications for performing an ASA. Most states have not. To determine if your state has a minimum qualifications for environmental professionals, contact your state environmental agency. The ASA process requires interdisciplinary skills, so it's difficult to prescribe a specific set of narrowly defined qualifications. Perhaps the best indicators of an environmental professional's qualifications are the combination of a specific experience and education of that individual. Experience that is specific to a type of property or issues to be assessed should weigh more heavily than other experience. When evaluating education and training, consider the academic background of individuals, but also review their commitment to continuing education and training. The ESA is a relatively new process that continues to evolve. It is critical that the environmental professional keep up to date with the latest standards and guidelines. The ASTM, Standard Practice for Environmental Site Assessments, Phase 1 Environmental Site Assessments, E1527, provides clear guidance with which to undertake an ESA, but also allows for the exercise of judgment and discretion by the environmental professional. The purpose of the assessment is to provide a standard that would allow property buyers and developers to meet the requirements established by the laws and courts to minimize the risks of environmental liability associated with buying property. The standard also can be used to evaluate final work product of the environmental professional. A checklist of the key points of this ASTM standard may be used to measure the completeness of report and work effort table 3.7. It should be noted that this checklist is not part of the ASTM standard guideline. The Phase 1 ESA is designed in principle to be cost-effective overview of a site that should identify indications of recognized environmental conditions. To keep the costs of the investigation at a reasonable level, typical Phase 1 ESA involves no collection or testing samples and is limited information already available through public sources, interviews, or first-hand observation. This approach allows buyer to determine whether there is an indication of a problem or an increased risk with a particular property. By limiting the scope of the ESA, the cost is minimized, but the conclusions of the environmental professional are drawn from limited information. The environmental professional may be unable to conclude that contamination is or not present, stating instead that there are indications of this condition or that circumstance which could indicate contamination. The ESA report should include copies of the notes collected during interviews, the database, review summaries, maps, aerial photos, and other reasonable documentation. Table 3.7, Site Analysis Checklist, Administrative Issues. Site condition. Developed existing buildings or structures. Former uses. Known site conditions. Character condition of existing roads. Points of access and egress. Approximate site distances. Expected road improvements. Visibility into and out of sight. Security considerations, neighboring property uses, existing rights of way or easement on properties, other encumbrances, condominium or community association. Zoning regulations. Zone identification, minimum lot size, front setback, back setback, side setback, one side total, permitted uses by right, permitted uses by special exception, maximum coverage, parking requirements, overlaying, zoning, sign requirements, right-of-way width, cartway width, curb requirements, sidewalk requirements, fence regulations, storage requirements, landscape ordinance. Land development regulations, street profile requirements, site distance requirements, slope restrictions, stormwater requirements, landscaping requirements, lighting requirements, Utilities access, distance to and connection requirements, natural gas, telephone, electricity, cable television, public water, sanitary sewage. Traffic, condition of local roads, access to site, internal circulation constraints. Impact on neighborhood, topography, general topographic character of site, areas of steep slope, aspect, orientation of slopes, site access, slope stability, soils, geology, soil types, depth to bedrock, depth to groundwater, seasonal high water table, engineering capabilities, class of soils, density, Atterberg, limit is compressibility, existing indication of slope instability, site erosion, sinkholes, fault zones, hydrology, sketch existing drainage pattern, off-site and on-site, presence of surface water features, quality of surface waters, floodplains, wetlands, riparian zones or floodplains, springs, wells, aquifer, anticipated drainage pattern, character and quality of receiving waters. Vegetation, wildlife, general types of existing vegetation, quality of vegetation, presence of known protected species, presence of valuable specimens or communities, presence of exotic invasive species, historic or cultural features, community interests, known historical features, unique natural features or character, existing parks or public areas, existing informal public access use on the site, community character such as architectural style conventions, local landscaping, local materials, environmental concerns, past site issues, neighboring site issues, evidence of field dumping or disposal, evidence of contamination, stained soil, stress, dead vegetation, etc., on-site storage, impact of site development on local water and air quality. The environmental professional is expected to exercise good judgment in the completion of the ESA and in some cases may elect to modify the ESA guidelines. While these changes are to be expected, deviations from the standard should be noted and explained to the buyer's satisfaction. Brownfields. Brownfields are abandoned or underutilized properties that are environmentally contaminated or are perceived as being contaminated from past industrial or commercial activities. Such sites may present a designer with a wide range of unfamiliar site restrictions and conditions. Site planning on such sites must address the contamination or the mitigation strategy selected to protect the users and the environment. Normal practices of site development and stormwater management may be restricted. In the past, site planning proceeded in the assumption that a site was clean. The designer was usually not involved in the remedial action design. Sites were cleaned up and then redevelopment occurred as if one clean site. To be effective, participants in a brownfield project, landscape architects and site engineers should be conversant with the environmental professional and understand the value and limitations of the site assessment. Further, knowledge of the state practicing the site remediation technologies will increase the opportunity for collaboration and innovative site design, enabling site designers to work closely with environmental professionals in the interest of the client and the environment. Table 3.8, Phase 1 Environmental Site Assessment Quality Assurance Review. The Phase 1 Site Assessment Guidelines Review Checklist is to be completed for the quality assurance purpose of verifying the substantive compliance of ESA report with the ASTM Standard of Practice for Environmental Site Assessments, Phase 1 Environmental Site Assessment Process E1527, except where otherwise noted. This review is based entirely on the report and does not include an independent confirmation or information. Records review. Does the report reference ASTM E1527? Was the ESA conducted by an environmental professional? Is a resume or statement of qualification attached? Were proper minimum search distances used in record search? Equivalent state lists. If proper minimum search distances were not used, was justification for each reduction and the new minimum distance provided? Did the environmental professional provide an opinion as to the significance of any listing as recognized environmental condition within the minimum search distances? Was a current USGS 7.5-minute topographic map used as the source of physical setting data? Sources used to determine the history of the site and surrounding areas: aerial photographs, local historic maps, historic USGS topographic maps, fire insurance maps, tax files, local records, interviews, 50-year chain of title, sidewalk cover. Did the environmental professional report any obstructions or obstacles that would prevent a thorough site reconnaissance? Was the exterior of the property visually and physically observed and the description included in the report? Was an inspection of the interior of the buildings conducted, including accessible common areas and representative sample of occupant areas? Was information from a prior ESA used in the report? Were changes between the earlier ESA and current observations noted? Were the uses and conditions of the site reported? Was the owner's representative present during the site visit? Were the interviews conducted? Did the owner provide any additional documentation regarding the site? Does the report include reference to site conditions not visually and physically observed by the environmental professional? Does the report include a description of the current site, use and conditions, a description of the adjoining property and uses conditions, a description of the topographic and hydrological conditions, a general description of the structures? Is the source of potable water identified? Are the locations of roads and parking areas described? Are past uses of the property discernible? Does the report include a conclusion or recommendations? Based on this review, does the ESA meet the standard guidelines?